Hi, my name is Laura Weiler, and I'm an undergraduate researcher with the Shepherd Group at the University of Iowa. I'm going to speak with you today about our research using machine learning to analyze the electron correlation energy. We perform coupled cluster doubles calculations on the uniform electron gas to begin our analysis of the electron correlation energy. The electron correlation energy is given by the difference between a given system's exact and Hartree-Fock energies. Post-Hartree-Fock methods such as coupled cluster are able to account for electron correlation energy to varying degrees of accuracy. The electron correlation energy is additionally given by the two-electron integral, or V of G, and the structure factor contribution, or S of G. While the two-electron integral is relatively computationally accessible, the structure factor is computationally expensive for large system sizes. We use machine learning algorithms to explore the structure factor's contribution to the electron correlation energy. Our exploration of machine learning algorithms in the context of making structure factor approximations has begun with Gaussian process regression. Gaussian process regression performs a non-parametric, probabilistic regression, which provides the advantage of not requiring initial assumptions about parameters, and instead creates a representation of the target function based on the input training data. Gaussian process regression thus computes a probability distribution over all possible fits to a given dataset, restricting the set of possible fits within confidence intervals as the size of the input data increases. Gaussian process regression is highly sensitive to the kernel specification, and thus a successful regression is largely dependent on the ability to successfully optimize kernel parameters. Shown here on the left is the radial basis function, or squared exponential kernel, with default parameters as provided by scikit-learn's Gaussian process regression module. Shown on the right is the result of training a Gaussian process regressor model on our structure factor data after optimizing kernel parameters. Given the incomplete set of structure factor data seen here on the left and an optimized radial basis function kernel, Gaussian process regression is able to generate the predicted function with uncertainty as pictured on the right. With Gaussian process regression, we hope to use relatively small system sizes to make predictions on the thermodynamic limit correlation energy. The electron correlation energy is an essential component of phenomena such as phase transitions. The ability to perform this kind of non-parametric regression thus has potential to impact the electronic structure theory and materials science communities. In fact, the next step of this project involves the application of Gaussian process regression to structure factor analysis on real systems. I would like to thank Tina Mim and Professor James Shepherd for advising this project. I would additionally like to thank the Shepherd Group, the University of Iowa, and the Iowa Informatics Initiative for providing essential resources and support. Thank you for watching.